All right. Good morning, everyone. So today in the topics in Sub-Riemannian geometry reading group, I'll present the Sub-Riemannian geodesics of the Affine-Additive group. We've already seen what is a Sub-Riemannian structure, what it means to have a Sub-Riemannian distance. This was done by Dimitris, and also Dimitris introduced us what is the Affine-Additive group. So at least the title should be somehow clear. To face this problem, we need to give some sort of background. The background involves optimal control theory, and this is the first part. We actually have other two parts. The second one, indeed, is the application of optimal control theory and the main theorem of optimal control theory, which will then allow us to study the geodesics in the sub-Riemannian spaces, both in the affine-additive group. Once we understand the technique of how to apply this principle in the affine-additive group, it will also be clear enough, and we can then just present the geodesics in the Heisenberg group. Then it will be, by knowing the ideas, kind of a continuation of this. And the last part is to study this kind of I don't know if we want to call it let's say surprise, as in the Euclidean setting. Ennio De Giorgi was the one who proved in large generality for domains, Euclidean domains, that the optimal isoperimetric uh, shape is the one of a ball. So one would expect that this type of phenomena also expands to other kind of metric spaces, but for this type of metric spaces, meaning the sub-Riemannian spaces, the CC sphere are not optimal isoperimetric set. We will see these in the Heisenberg group. And for looking at this, since there are some reasonings and things I want to make sure that both Dimitris and Georgios follow me, I will present this in a hybrid way, so not with slides, but by writing it down and see the consequences of this step by step. Okay, while for the first two parts, there is slides. Okay, so we can begin with optimal control theory. I quickly recall what a control system consists of, and this is first an ODE, okay? So it's x dot equal f of x and u, where f is a function from Rn to Rk, and u is some measurable function from the interval 0t to Rk. And this is typically not a curve. It could have a lot of issues in terms of continuity, so that's why I prefer to refer to this as a measurable function. And so once we have fixed this measurable function and then initial data x0, we can get a solution for the ODE, and this we call it trajectory associated to the control. And now we actually give a name, and this is control for you. So given this, we also fix some payoff functional. This is the reason why it is with a capital letter P. And this payoff functional depends on some function inside R, which we call it running payoff. There could also be another term, an extra term outside of the integral, which sometimes they denote it as a terminal payoff, on endpoint payoff. But for our problem today, we don't need to consider that, so I just put it as it is. I think it's also worth to mention where this theory developed. this theory developed in Moscow thanks to the big study of Pontryagin and his students. Among them, we can consider Boltiansky. And there is, I mean, from what it is said, I can tell you, this letter U is not just random choice. It means that it's actually the beginning of the word upravlenia in Russian, which means control. So this is not really the official reason, but after discussion with also some other colleagues, we claim that it could be the reason why U is the letter associated to controls. Okay, we can keep going. And yeah, now we need a bit of notation. We consider kind of the dual of the letter X. We give it a Greek type of alphabet, and so we put Xi. So Xi will be the dual part of X. And we also fix some X0, and we call Xi bar to be just simply the vector with coordinates Xi0, which is real, and the other vector Xi. To this, then we can introduce the Hamiltonian. And this Hamiltonian keeps track of the control problem, as you can see, because here we have a dot product between the vector field to which x dot is equal to, and here we also keep track of the running payoff. Now we are in position to present what is the Pontryagin maximum principle. Later I will refer to this as the PMP. And so this theorem gives us necessary condition for an optimal control, and so for an optimal trajectory. So if we have an optimal trajectory, it satisfies a certain amount of conditions. And yeah, I will read with you the conditions. So if V is an optimal control, then we have a multiplier, and the multiplier has this dependence on the control V, okay, so Xi bar V, which is non-zero. So let's remember this assumption, where the zero component of the vector is either 0 or 1, and Xi V is an absolutely continuous curve. Okay, so if it's absolutely continuous, it's by Rademacher's theorem differentiable almost everywhere. And this explains condition 2, why we can write it down almost everywhere. And this condition 2 is that the Xi dot of E is equal to minus the gradient with respect to the variable x. Okay, so this one of the Hamiltonian. I also now want to call attention to the first of these consequences. So essentially, the multiplier or costate curve has a certain type of property. So we have that the optimal control is attaining the minimum of the Hamiltonian. So I'm giving the formulation of the Pontryagin maximum principle, but we are caring about minimizers this time. I mean, one could just replace the minimum with minus the maximum. Okay, so. And the last condition is that the Hamiltonian, when we consider the optimal trajectory on this is constantly equal to some amount h. Good. So this is the Pontryagin maximum principle and the three kind of necessary conditions for an optimal trajectory. So now we can switch to the next type of part, which is the Sub-Riemannian distance on AA. This was already introduced by Dimitris. I just want to focus on the Sub-Riemannian distance, where on the left, I have the neutral element. indeed, when we study geodesics, we know that left translations are isometries. So we can always study first this problem and then just left translate it to study other type of geodesics on our space. And so yeah, our space is a length space, and actually it's also nice what Dimitris told us last week, that we have a Choroshevsky theorem. This actually tells us that this infimum along the length is not an infimum, but is actually attained, and so we can write it as a minimum. And here we have our usual length of a curve. The curve that where we infimize or minimize are horizontal, and yeah, we can write them like this. And the constraint are indeed that the endpoints, so the points that have to be joined, are the neutral element and P. Great. So we can go forward. So essentially, the length minimizing property of the curve realizing the distance is equivalent to this contour problem. We can see why. So first of all, we wanted to minimize some distance, right? That is this minimum here. Good. So what we minimize now is this functional that is equivalent, providing that lambda dot is equal to 2 lambda u1 and t dot is equal to 2 lambda u2. So this essentially is just a rewriting of the minimizing problem. This last condition here is actually the horizontality condition. So this is how we get back the equivalency, because here we are minimizing among horizontal curves. And the two conditions that we have two endpoints, E and P. So the problem that we are trying to study is makes sense when P is not the neutral element, otherwise the curve would be constant. So let's also remember this other condition, that P is not equal to E. Good. Yeah, so minimizing this type of functional, so the one with the root, is a bit complicated. As you can see, when we have a presence of a root, we also have issues with the regularity. Like in terms of controls, this is not smooth. And applying the Pontryagin maximum principle to this won't be that won't give us the most straightforward or easy to tame ODEs. So we need to kind of see the problem on a different viewpoint. And this is essentially the second viewpoint. So create this other functional, which instead of being the length functional, it's called energy functional. So the difference between the two is this rescaling 1/2 and the absence of root. These three conditions are the same, and these as well. So what I wanted to say also regarding to this is that essentially, like, just to motivate quickly why we have this proposition. So the control problem 5 and 6 are equivalent. Well, essentially, we are considering horizontal curves. So these curves are rectifiable from a very basic result in metric spaces. You can see that the rectifiable curves can be reparametrized by arc length. So essentially, this gives you a sort of constant speed. Now, combining this knowledge with the information that with another condition, which is either a Jensen inequality or a Cauchy-Schwarz inequality. So by knowing these two things, we can actually see quite straightforwardly that these two problems are equivalent. I just check. Do we have any questions so far in the chat or anything? so clear, it seems. Okay. So yeah, we can go forward. So now, if we have this control problem, the Hamiltonian reads as you can see. So we have, I want to go back to show you what the Hamiltonian is. So it's this dot product between f and psi, and then we subtract psi 0 times the running payoff. The running payoff now, it's this 1/2 and this much. Very good. So here is where the running payoff takes part, and this other part is the dot product between psi and the vector field f. Okay, so as we can see, so our x is a lambda and t, but the dependence on a and t is missing. I mean, is missing, but we also have horizontality conditions and dot derivative. But apparently, this Hamiltonian doesn't seem to depend on A and T. And yeah, the control U has two entries, U1 and U2. Good. So now I want to address another type of issue, uh, the issue of this psi 0 here. So essentially, if we use the Pontryagin maximum principle, which I want you to check again, this tells us that psi 0 could be either 0 or 1. But when psi 0 is 0, this Hamiltonian reduces to this part. So we are essentially neglecting the running payoff, which is very essential in our minimizing because it's really the part that keeps track of of the curve being a geodesic. So it's a very big open problem in sub-Riemannian geometry to study which curves when xi is equal 0 are still geodesics. And it's actually convenient for us to see if we can prevent this problem by looking at our Hamiltonian and find a condition that actually tells us, no, xi 0 won't be 0, xi 0 will be 1. And these two conditions, psi 0 equals 0, is called abnormal case, and the case when psi 0 is 1 is called normal. So this proposition essentially, so let V be an optimal control for the problem 6. So it's the problem with the energy. Great. Then V is a normal control. Okay. So to see this more in detail, I think it's important, especially for Georgos and Dimitris, to see a proof and to see how maybe it is flexible enough also for other scenarios or contexts, sub-Riemannian contexts, like the Affine-Additive group with a larger dimension. And so, yes, if we assume that xi 0 is 0, essentially the Hamiltonian reduces only to the first part. And you can see that I did some sort of rearranging of this first part. How did I do it? I factored U1, which appears only here, and I factored U2, which appears here and there. Good. So essentially, I rewrote my Hamiltonian as some sort of dot product with a control. Why so? Because we really see in this way that the Hamiltonian independence of controls is linear, so it's a linear function. So if we look at this condition 2 in Pontryagin maximum principle, which tells us that if we have an optimal control, this attains the minimum over u in our case in R2 for the Hamiltonian. But if the Hamiltonian is a linear function and we want the minimum to exist, well, we know that the minimum of linear functions is often minus infinity, unless we impose that the Hamiltonian is actually identically zero, then the minimum actually is attained. And so to attain the minimum, we write down these two conditions. But these two conditions, with straightforward calculations or observations, contradicts with this, which was a fundamental assumption in the Pontryagin maximum principle. So the fact that the multiplier is not identically zero. And or if it doesn't contradict with this, we can actually see that it contradicts with the condition that the starting point and the end point are different. So I see that there is a discussion in the chat. Yeah, exactly, Yanis. Yeah. Okay, we will talk about this later, but yeah. Yeah. Okay, so I keep going. Um, so I keep going with presenting this theorem. This theorem, I obtained it in my thesis. So in my PhD thesis. So essentially, once we have ruled out the abnormal issue, we can actually see what are the Sub-Riemannian geodesics. So if we take a curve, okay, in the interval 0t on the Affine-Additive group, and we take some initial data. So the initial data are the condition that gamma 0 is equal to the neutral element, and this type of co-state condition, which is related to the multiplier of co-state psi. Then we have a case distinction. So this essentially comes directly by studying the Pontryagin maximum principle and see this type of necessary conditions that we have here. So if we have that the control is a minimizer for the Hamiltonian, uh, we see that the gradient with respect to the control u here is zero. So from this we have some conditions. We also have some conditions here from this co-state equation. And so from these two equations, we can actually obtain these results that goes into this case distinction. So if our initial co-state data has both these two entries equal zero, then the curve is actually a line. But if xi02 is non-zero and xi03 is zero, this seems not to be a line in the sense on the affine-additive group, but if we project it to the hyperbolic half plane, we actually see, so projecting means we don't look at this coordinate, we see that there is some sort of exponential dependence in S here and there, so it's some sort of hyperbolic line, hyperbolic geodesic. It's a lift of an hyperbolic geodesic. As I guess there is something in the yeah, exactly. So this is absolutely natural lifts of hyperbolic circles. Yes, exactly. So essentially we are lifting geodesics of the hyperbolic plane. And the last case again is another type of geodesics of the hyperbolic plane is a circle and a lift of it. So if xi03 is not zero, then we have that gamma is an horizontal curve where the projection on the hyperbolic plane gives us on this part and on this part a constraint, which is the constraint of being a circle. Okay, so for the moment, we have this result, which tells us what are the geodesics on the affine-additive group. The second part would be similar in the sense of presenting what are the geodesics on the Heisenberg group. The method is as it was showed before, writing down a Hamiltonian, prove that the optimal control also in the Heisenberg group is a normal control, and then we have this result. So if we have a Sub-Riemannian geodesic, now we parameterize in the interval 0, 1. and with the initial data. So it begins from the neutral element of the Heisenberg group, and we have as a co-state, initial co-state condition this. So the first entry is sine theta, the second cos theta, and then here we have phi over 4, where theta and phi are in this range. Then we have this case distinction. So if phi is equal 0, then we have lines that stay on the xy plane. If a phi is not 0, then we have this type of curves. Okay, so psi s is this ratio, ys is this other ratio, and ts as well. So um, this is a theorem which was given by Monti in the 2000s. Um, the principle and the ideas behind this theorem indeed are make use of the Pontryagin maximum principle, but in his work he also proves something more, which is the third part of today's presentation. For doing it, I will switch to sharing it on the notes, and we will try to kind of argue on these conditions step by step, so you can follow me, and if you want, either take notes or I'll pass you my notes later. So now I share the screen with the other account, and let me know if it works. Okay, so it says I have to stop sharing with this one. Okay, good. Now I try to share here. Yeah. Okay, great. Okay, so we are back. We can look after these geodesics in the Heisenberg group. So I will just rewrite them again and study the situation of the CC sphere. So we had that gamma is a curve from 0, 1 into Heisenberg, right? We know that gamma 0 is actually the identity neutral element of the group. And I want to focus on the case where phi is not 0 for the moment, okay? Essentially because the other curves are lines laying on the xy plane. So this is looking like a part that has not much in terms of measure on the group, but these curves have a larger impact. So yeah, if we write down what is xs, ts, and xs, ys, and ts, and I'll write this down very quickly. Here we take cosine of theta, 1 minus cosine of phi s. Here we have sine of theta, sine of phi s. And here we divide by phi. And here if we write sine theta, 1 minus cosine of phi s plus cosine theta sine phi s. Good. And here we divide again by phi. And here the last thing is phi s minus sine phi s over phi squared. Okay, so now the reasoning I want to begin with is where is the endpoint of the geodesic laying on? So the endpoint for s equal 1, right? Because that is our interval. Well, this lays on the CC sphere of center, well, the identity element and radius 1. And another thing I want to say extra is that if we replace then this S, so I just write it again very quickly, it won't take us too much time. If I rewrite this down, we obtain something very interesting. So what is this for S equal 1? This actually is a parametrization of the CC sphere, which depends only on theta and phi. Now give me a second. I just erase the dependence on S. Let me check for a second that I erase all the dependence. Okay, good. So we erased all the dependence. This is a parametrization of the CC sphere. Okay, it's a surface patch, is missing some parts, but it's I mean, because indeed we have to consider theta and phi in open intervals, but we can cover it. We can cover the CC sphere by patches of this type and this line laying on the XY plane. But what does this parameterization look like? Well, this parameterization looks like very regular. It's indeed a C1 smooth parameterization. So this is how Monti proved that the CC sphere in the Heisenberg group is C1 regular. So the CC sphere in Heisenberg is C1 smooth. Um, Now, another things, other couple of things I want to say is that we can actually draw this surface for a moment to see how it looks like. And this will be helpful for the third part of the presentation. So essentially, this sphere looks like this sphere looks a bit like an apple. So I also want to draw what is inside. And as you saw, this type of parameterization is C1 smooth, so we don't really have continuity cuts, but okay, so basically this goes down continuously, okay, this goes down continuously down here, and as well, this goes up continuously. But we have some sort of cusp here, okay? Good. The cusp, I should make it a little bit pointy because we really need, is not that smooth at all. And yeah. So remember that, okay, it looks like an apple. It looks like an apple, and here is the identity element. This is, I don't know how accurate, but this is what corresponds the vertical axis, so the center of the group. And we actually see, I mean, maybe the drawing doesn't present it that accurately, but this surface has a symmetry, and this symmetry is given by the fact that the isometries of the Heisenberg group, among them, we have a rotation around the vertical axis. And okay, so Now that we have a drawing, we can actually consider the isoperimetric problem. Okay. And I mean, this third part has a purpose. The purpose is that CC spheres in the Heisenberg group are not optimal sets. Okay, so to see this, we need some considerations. These considerations are all based on remarks and things that were showed either by Dimitris or Georgios in previous presentations. So I will give a quick overview. So, well, this first part, I don't know if it actually was showed by them, but I still want to say it. So there is some sort of dual formulation. For the isoperimetric problem, we can either maximize the volume, okay, where this maximization is under a fixed perimeter, but this formulation has a dual analog under enough regularity for the sets with this other problem, which is minimizing the perimeter for a fixed volume. Okay? So one can either present maximizing the volume for fixed perimeter or minimizing the perimeter under a fixed volume. That's interesting because indeed what Monty does in his work will reflect on this right-hand side, but for us to convince us why this is true, we will look at the left-hand side, okay? This is actually indeed the Dido problem, the one on the left, the one we present. But in the paper is proved with the thing on the right. So the two facts that I need from Dimitris and Georgios lectures, well, one is I think surely was given by Georgios and was the invariance of the perimeter and volume. I mean, actually, that's not accurate to say it this way. It's more some sort of scaling of perimeter and volume under dilation. And the other is that we can see the CC ball as a dilation of radius r of the unitary ball. So if we actually want to present this problem and show that the spheres are not optimal sets because of the scale invariance or this scale well behavior, and because the CC sphere indeed the radius scales like this, we can just present the argument and the topic for the one CC sphere, so the CC sphere of radius 1. To present the non-optimality. Okay, so now I guess we can look a bit again after this sphere and underline some parts of it that are really interesting. So what is my purpose now? My purpose now is to, let's say, if by contradiction, okay, so suppose that SCC of E1, well, okay, so then there is a typo here, is the optimal isoperimetric set. Okay, we will construct, this is what we're going to do, we will construct a set. So this is our goal with same perimeter, but larger volume. So this is essentially what we're going to do. And this will contradict the fact that the sphere is the optimal isoperimetric set. How can we do this? So I want to use some colors to help us into identifying some areas. So do you see this part of the sphere here, which is some sort of part that begins when the sphere starts to go up again and create this cusp. And look at this other part, which is the part where we approach the other cusp, but from below. Okay, so consider these two parts. And really, if you keep having an apple in mind, you can really easily see these things. Okay, so a thing that Georgios showed us is that if we do so essentially we will split this sphere in three parts. The white part, which stays as it is, the red part, which will translate and create a new part of the sphere, and this other part which translates and create another part of the sphere. I recall you that these translations are not just simple Euclidean translations. These are Heisenberg translations. If they move along the vertical axis, they are left translations. So this type of left translation is moving uh, this green part up and the red part down. Now I show you how. Uh, okay, with the next figure. So now we need to erase something. Give me a moment, be patient. So this surface is, again, I recall C1 smooth. So it's very continuous. All these type of gluing I'm about to do are continuous type of gluings. So there is no worry for our surface to ruin. Or if it ruins in a sort of measure zero parts. So I wanted to left translate the green part up. Indeed, I will do it. So I will translate it up until here. So now we go up. And here we translate it down. So now we go down like this. So now Georgios showed us that the perimeter doesn't change with the left translations. So the perimeter is a measure, so it decomposes well. So the perimeter of this sphere is the same as the perimeter of this other sphere. I guess you can see why. So this part is just a left translation. So how do we denote this? Okay, left translation of then it's this amount here, which is the same as this amount here, which now, oops, sorry. So the same as this amount here, where here we have the neutral element. And this amount for the moment, I mean, I can be more technical, but I guess you can also read these details directly in the paper. And this amount, I want to call it, let's say, H. So this is a left translation of value 00H, okay, of this of the green cusp. So L of this part that I will just call it C in green, okay? And this as well, it's a left translation, the one below, of 00, now not H, but should be, well, the inverse of this translation. Of the other cusp. Okay, good. So nice. What's happening now when we move down this part? Thanks to what Georgios showed us last time, has same perimeter. The part in green has also same perimeter. The part in blue is the same as before. So the conclusion is that the perimeter doesn't change. But actually, if we recall how the sphere looked like from inside, which was this type of thing, okay? We see that the volume of the region bounded by the CC sphere is smaller, strictly smaller than the volume of this new object. So we actually have constructed a set that has a larger volume but same perimeter. This means that the metric sphere in Heisenberg group are not optimal. So conclusion. The sphere in H is not. The CC spheres, okay, we can say are then not optimal. Isoperimetric sets. Okay, so yeah, on my side, I'm done. So thanks for the attention. And I guess we can pass to the questions if you have any. And yeah.